Welcome back, students. In this video segment, we will cover two sections that are very, very closely related. Although in the textbook, they're kind of far apart. We're going to look at sections 15.5, surface area, and 16.7, surface integrals. Again, two very, very closely related sections. Okay, so let's get started with section 15.5. In this section, we have the fundamental problem of finding the surface area of a portion of a surface. So let's get real formal here. Given a function z equals g of xy, find the surface area of the portion of the surface that lies above the region D in the xy plane. So if you can picture in the first, or view in the first octant, a kind of a lime wedge, the wedge of a piece of citrus in the first octant. The region D would be the quarter of a circle in the first quadrant of the xy plane, and I'm interested in the surface area above D. Okay, so what we're going to do is we're going to use the same type of calculus that we did to find areas, volumes, and arc length. What we're going to do is we're going to imagine dividing the surface into an infinite number of small patches of surface having area ds. ds for an infinitely small surface area. So I've got that pictured for us in green. I've sort of sliced off a sort of heavily green markered patch of area ds. Okay, so let's find this differential element of surface area ds. So the next thing I'm going to do is I'm going to get x and y involved here. So take a look off to the right here. We're going to need a nice little result from Calc 1. Although you may not have seen this in Calc 1, we could very easily get it from just using the concept of the derivative as the slope of the tangent line. So suppose we're given some function y equals f of x, and at some point we have a tangent line, some point on the curve, and then we move from the tangent line a small distance dx horizontally. The distance we would have to move to return to the tangent line, I claim, would be y prime dx, the slope of the tangent line times dx. And that's easy to see because we know that slope equals rise over run. So if we take that y prime dx, the rise, and divide it by the run, the dx's cancel and we get y prime. It's a really nifty way of connecting rise and run with the derivative. Well, we're going to do that with our little patch ds, but it's a little bit, and actually it's quite a bit more complicated. But the idea is basically the same. So the idea is that the surface area of that little patch is approximately equal to the surface area of the tiny portion of the tangent plane that lies directly above the patch of area ds. Okay, and if you missed that, don't sweat it. I'm going to draw that in. So at one corner, the upper corner of that little patch ds, I'm going to draw a little portion of the tangent plane, but only that portion of the tangent plane that lies above, let me redo this, above the patch of surface area ds. So here's that little piece of the tangent plane I'm drawing. Okay, little piece that just lies directly above the green patch of surface area ds. Okay, so you see a little blue patch of surface area. I want to find the area of that piece of the tangent plane. Now, the area of that piece of the tangent plane is not going to be exactly equal to ds, the area of the little green patch, but we're assuming that ds is infinitely small. So an argument could be made that the error in using the tangent plane to estimate that area is infinitely small. That is 0. Okay, and this strange concept of making the error 0 just by making the patch infinitely small can be made really, really mathematically solid. And physicists use this device all the time. So let's find the little area, the area of the little portion of the tangent plane that lies directly above the little green ds. Okay, so what I'm going to do next is I'm going to draw a couple of vectors along the edges of that little piece of the tangent plane. Okay, so I'm going to draw a little red vector along the edge. A little red vector. I'm trying to make it solid so it really shows up. And I'm going to draw another little red vector along another edge of that little piece of the tangent plane. And I need to find the formula for those little red vectors, because once I find the formula for those little red vectors, I can cross those little red vectors, and that cross product will equal the area of the little blue patch of tangent plane, which is our approximation to the little green patch, ds. Okay, so why is that true? Why is it true that the cross product of those two vectors will give you the area of the blue tangent plane patch? Because if you remember from way back, the beginning of the course, if we have two vectors, a and b, that geometrically, we talked about it I talked about it in video lecture for about 2 minutes or less, is one of the applications of the cross product. But the area of the parallelogram is equal to the magnitude of the cross product. Okay, so I need those two little red vectors. So what I'm going to do is I'm going to go up to the corner, and again the little patch where the two red vectors are tail to tail, and I'm going to find the vector on the left first. In order to find the vector on the left, I'm going to move in the x direction dx, and then I'm going to come down in the z direction to get to the tip of the vector. And I know this is small. We have a little right angle formed there. Okay, so let's call that vector A. We'll call the other one B. So let's write out the components of A. A has x component dx. It has no y component. Our formation of the vectors is purely in the x and z direction. Now, what is the z component of this vector? To get the z component of the vector, I'm going to use that little piece of information that I got from Calc 1 that says if you move a little dx, that to get back to the tangent line, it's the slope times dx, y prime dx. So if I move, now back to our drawing in 3D, if I move a little dx to get back to the line, well, that's in the x direction holding y constant. So that's forming a tangent line, if you will, holding y constant. Oops, let me get rid of this. That's too heavy of a pen. If I continue that vector, or a line along that vector, that's a tangent line in the x direction. What's the slope in the x direction? It's exactly the derivative with respect to x times dx. So it's g sub x dx. Remember, the partial of g with respect to x is the slope in the x direction holding y constant. So let's find the vector b. And believe me, you won't have to derive this formula. However, the surface area of the little patch is so important for the rest of our semester, literally the rest of our semester, that we really need to be careful and that we understand how the little ds is formed. So I want the vector b, and I erased it off so I could draw in my drawing. I'm going to do the same thing as I did for a. Although I'm going to move in the y direction. Y direction, a small distance dy, or displacement dy. And I'm going to turn 90 degrees and come back to the sort of the tangent line along which that second vector lies. Okay, so let's form the components of that vector. There is no x, or the x component is 0. I'm not moving in the x direction. The y component is dy. So I need to move from that displaced value dy back down to the vector b. Well, that tangent line along which I can place that vector b is in the y direction. And the slope with respect to y is the partial derivative with respect to y times dy. This is the hardest part of the derivation. It's over. The rest is now purely computational. Okay, so I want the surface area, the little ds. That little ds is equal to, because it's so small, the area of the patch of the tangent plane, which is the length of a cross b. So let's find the length of a cross b. So it's the length of the vector a cross b. Now let's form a cross b. I, j, k, the standard basis vectors, a dx, 0, g sub x dx, b vector, 0, dy, g sub y, dy. By the way, the author of your textbook does not derive this vector this way. There's a close relationship, or it looks close, but it's not quite the same thing. He uses delta x's and delta y's. I pass to the limit as the number of patches goes to infinity to make them infinitely small right away. So I replace delta x with dx and delta y with dy. Okay. In any case, let's continue this computation. I'm looking at the length of the vector, and let's perform this computation. If I cover up the first column, I'm going to have 0 times g sub y dy minus, and then g sub x dx dy. If I cover up the second column, just taking the dot product, you can verify this by stopping the video and taking a critical look yourself if you'd like. You don't have to go at the pace that I'm going. You can even click, I think I mentioned this, in the video settings, you could slow down my talking, which is really bizarre. I actually speed it up when I review my videos once in a while. I speed up my talking because I don't need to hear me talking so slow. But you can slow my talking down, and for somehow, I don't know how they do it, but YouTube slows down the talking, but doesn't make the voice lower. It keeps my same pitch, which is really bizarre. It's not intuitive at all to me. Okay, I'm getting way away here. So if I cover up the first column, then take the determinant of the 2x2 matrix or the 2x2 determinant that's formed by doing that, by covering up the third column and the first row. Standard operating procedure for us here. Okay, now that dx dy is a scalar within this expression, so I'm going to factor it out. So it really looks like I'm finding the magnitude of gx minus gy 1 dx dy, assuming my displacements dx and dy are positive. Okay. Now let's take this magnitude. This is the square root of, I'm rearranging the order, of course, not of course, but so it's 1 plus gx squared, negative gx squared, which is positive g sub x squared, also g sub y squared. And that dx dy can be considered a small dA in the xy plane. I think it would probably be mess up my drawing to try to draw that in, but I'll give it a shot. Okay, so trying to isolate the little dx times dy. It might actually turn out. It's actually turning out. I didn't think it was going to turn out very nice to see. So there's my dA. It's that little dx dy. It's the area of the projection of the little patch ds into the xy plane. Okay. So in any case, this is something you want to memorize, not the proof at all. You don't need to memorize that. I won't test you on that. However, you should memorize this differential element of surface area. It's going to follow us. It's going to follow us to our last few lectures in the course. So I think I'll put it in nice red. Okay. So the differential element of surface area is the square root of 1 plus the derivative of the surface, if you will, if z equals g of xy, g of xy, of course, g sub x squared plus g sub y squared times dA. Okay. So how do we get the total surface area? We add up all the little ds's. So the total surface area equals, we integrate, and this integral is a double integral. Why? Because dA, the dA portion of our differential element of surface area is the dA that we have in our double integrals. It's a double integral of 1 plus g sub x squared plus g sub y squared dA. And we integrate that over the region in the xy plane d. Okay. Now we don't have to use the variable g. We could also write this as the double integral of 1 plus, if you want, z sub x squared plus z sub y squared dA. Okay. So we're going to do one example. We're going to do we only need to do one example because this next section that we're going to look at, and it's a rather long section, but the next section uses ds over and over and over and over again. So we'll be seeing this for the next I don't know how long this is going to take, hour and something. So here's our problem. Here's our next example, our first example. Find the surface area of the portion of the sphere x squared plus y squared plus z squared equals 16 that lies above the plane z equals 1. So let's take a look at that. So I tried to draw a little portion of upper portion of a sphere, upper part of a sphere, upper hemisphere. And there's a green plane going through it at z equals 1. This is not to scale, of course, because the radius of the sphere is 4, so it should be, the slice should take place a lot lower than this, but I kind of have to use our imagination here with my poor drawing skills. Okay, so the surface area, let's just say SA for surface area, equals the double integral over the region in the xy's, the projection of the region in the xy plane, D, and we'll get to that in a minute, of ds, the sum of all the ds's, or the double integral of the square root of 1 plus z sub x squared plus z sub y squared dA. Okay. where that d, now let's return to the d. The d is the projection of the surface here, the surface that we're looking at that winds up in the xy plane, the projection in the xy plane. So I'll go back to green for that. So right below this sort of cap of the sphere is the intersection of the sphere and the plane z equals 1 that's put into the xy plane or knocked down into the xy plane. That's d. And that should be a circle. Okay, so we're integrating doubly over a circle in the xy plane. Okay, so let's find that. Let's find that integration. Let's find that region D. So let's do that right now. Region D corresponds to the intersection of x squared plus y squared equals 16. X squared plus y squared plus z squared equals 16, and z equals 1. Well, if I substitute z equals 1 into the plane, into the sphere, I get x squared plus y squared plus 1 squared equals 16, or x squared plus y squared equals 15, which is a circle. That little circle is x squared plus y squared equals 15. Okay. Now I'm going to need my little ds. I'm going to need my ds, so let's find that. ds is the square root of 1 plus the partial derivative of z with respect to x, z on the surface with respect to x squared plus partial z partial y squared. Well, let's go to our surface. Our surface then was x squared, or is x squared plus y squared plus z squared equals 16. That's our surface. So z equals 16 minus x squared minus y squared to the 1/2 power. And it's the positive square root since we're looking at the upper hemisphere. Okay. And I solved for z because we kind of need zx and zy. So what is zx? Z sub x is 1/2 16 minus x squared minus y squared to the negative 1/2 times by the chain rule, the derivative, partial derivative of the inside with respect to x. So this is negative x over the square root of 16 minus x squared minus y squared. Now the partial of z with respect to y will be very similar. The partial of z with respect to y will just contain negative y in the numerator, so I really don't have to do that separately. So let's continue with this. This is, the surface area is the double integral of the square root of 1 plus z sub x squared. A little writing going on here. Z sub x squared, if I can fit this in here, plus, I think we'll fit, z sub y, negative y over the square root of 16 minus x squared minus y squared squared, square root of all that, dA over the region D. Okay, so let's simplify that integrand before we start converting this double integral into an iterated integral. So d. Now, when you square those terms, you're going to get x squared plus y squared over the same denominator. So you're going to get 1 plus x squared plus y squared over 16 minus x squared minus y squared dA. A bunch of algebra. Okay. Now, if you make that 1 into 16 minus x squared minus y squared over itself, then this simplifies even further. Okay, so if you make that 1 into 16 minus x squared minus y squared over itself, which I just by magic went off camera and put in, you get, you get double integral over d. The only thing that remains in the numerator is 16, and the square root of 16 is 4. Over the square root of 16 minus x squared minus y squared dA. That integrand, that's our ds, and I'm gonna write that out separately because we're going to need that little ds in the next, for the lecture for the next section. I've chosen examples in the next lecture, or the next section, that involve this same sphere. Okay, so the differential element of surface area for this particular sphere, we're going to recycle. So just to put it, kind of put it in the back of our minds right now. Not too far back though. Okay, so how do we evaluate this integral? This is a double integral. This is nothing more than a double integral that takes us back to early in chapter 15. Not too early though, because and that's your hint. It's not too early, because there's a really important alternative to rectangular coordinates that we should use, and by now you probably figured that out before I even said it. We're integrating, D is over a circle. We're integrating over a circle, and x squared plus y squared is r squared. So it seems real natural to go directly into polar and convert this into a doubly integrated, a doubly iterated integral in polar coordinates. So I'm going to do that right away. So x squared plus y squared equals r squared. So this is 4 over the square root of 16 minus r squared. dA is, find my mistake. Find my mistake if you can. dA dr d theta. Good. I'm assuming that you found it. It's r dr d theta. We'll forget that little extra r. Okay. Now, what does the region D look like? The region D is nothing more than the circle x squared plus y squared equals 15. It's a circle centered at the origin of radius radical 15. So the equation is simply r equals radical 15. So to get that entire circle, r goes from 0, the origin, to the edge of the region D, and theta goes all the way around to sweep out the entire circle. Okay. Now this integral is very simple to evaluate. In fact, it just involves u substitution. So I'm going to do it, but you can feel free to speed up the video through the actual integration if you want. It's very simple if you see the u substitution, but I'll do it off to the side here. So let's do that. I'm going to do this off to the side here. I'm going to integrate, let's see what I want to do, r over the square root of 16 minus r squared dr. The u substitution is 16 minus r squared. du equals negative 2r dr. So our integral becomes, well, r dr is then negative 1/2 du, negative 1/2 du over the square root of u, or negative 1/2 times the integral of u to the negative 1/2 with respect to u. Adding 1 to the exponent, you get u to the negative 1/2 plus 1 is 1/2 over 1/2. Okay, so this becomes minus u to the 1/2 plus a constant, or minus the square root of 16 minus r squared plus a constant. So there's the off to the side in a cloud sort of integration of this, of the antiderivative of the innermost integral. So we have the integral from 0 to 2 pi, and the fundamental theorem says we integrate, and I'm going to bring our integration work in without the constant of integration. This is as r goes from 0 to radical 15. Then we integrate that with respect to theta afterwards. When I substitute the square root of 15, I get 16 minus 15 is 1. When I substitute 0, I get the square root of 16, which is 4. Or the integral from 0 to 2 pi, so super simple integral of 12 d theta, or 12 theta from 0 to 2 pi, or 24 pi. And what are the units? What are the units of this thing? What did we just find? Surface area. Area. So these are square units. Square units of area. Okay. And that ends section 15.5. We're going to enter a very long section, so you might want to plan on a break somewhere either now or in the middle of section 16.7 coming up. Without further ado, let's start section 16.7. So let's dig in. Let's dig into section 16.7, surface integrals. There's some good news here. The good news is that the concept of a surface integral is just an extension of the kind of thing we were doing when we found surface area. In fact, surface area, the integral that we get for surface area, is a special case of a surface integral. It is actually a surface integral. Okay, very much like the arc length of of a portion of a curve is a special case of a line integral. Okay, so let's define a surface integral more generally. We start out with the same picture. We have a surface. We imagine dividing up the surface S into an infinite number of small patches of surface area ds. So it looks like we're doing the same thing so far as we did with surface area. Okay. Then here's where we do the generalization. At some point in or on the little patch of surface area ds, and I'll just put it up at the upper corner here. It doesn't have to be. I'm going to place a point xyz. My x doesn't turn out real nice now. X, Y, Z. And the first thing we do is we sample some function. And it's not the surface. The surface has equation z equals some g of xy. We sample some additional function, some different function, and the function is not of two variables. The function is three variables. We sample f of x, y, z. We sample the function f at the point x, y, z. So just to slow down just a little bit, we have a surface z equals g of x, y, and we have some other function. And we don't have to give units to that function. We'll get some physical idea of what's going on with this stuff in a bit. But we have some additional function. This function is of three variables, f of x, y, and z. And we sample the function at some point either in or on that little patch of surface area ds. Then we multiply. We're doing a very similar thing that we did with line integrals. We multiply the value of that function, f of x, y, z, times the surface area, ds. Okay, and I think, actually, I know that we looked at a couple of really interesting application problems with respect to mass and for line integrals and stuff. This could also be a similar application. The f of x, y, z could be the density of the surface at a point. So it could be the mass per unit surface area at the point x, y, z. If we multiply that by the small ds, we get the approximate mass of the patch of surface area ds, and then we add those up and we get the total mass. It's that adding up that gives us this thing called a surface area. This thing called a surface integral. So we integrate over the entire surface. We integrate over the entire surface. S to form this thing called a surface integral. To form the surface integral, this kind of abstract quantity for now. The surface integral is defined as double integral symbol over S, not over the projection, but over the surface of f of x, y, z ds, where ds is the same differential element of surface area that we looked at in the last section. Okay. So if f of x, y, z is 1, if f of x, y, z is 1, we have the last section. We have surface area. So just like line integrals, though, we need a method for evaluating surface integrals. So how do we evaluate line integrals? Think about it for a minute. How did we evaluate line integrals? We found a parameterization of the curve. Then we stuffed the curve into the integral and turned it into a Riemann integral. Okay, we spent a lot of time doing that. We spent a lot of time avoiding doing that with conservative forces and stuff like that, or conservative fields. But that's how you evaluate directly a line integral. We do the same thing for surface integrals. Same type of thing. Okay, let me be much more specific. So how to evaluate surface integrals? Consider that we're integrating, or rather we're given the surface z equals some g of xy, where xy comes from the domain and the xy plane. Again, we do a similar thing we did with line integrals. We stuff the formula for the surface into the surface integral and then evaluate over d. Okay, so I'm going to be real explicit here. The surface integral, the surface integral of f of x, y, z ds, to evaluate it, we stuff the formula for the surface into the function, into the integral. So f of x, y, and z is g of xy, but ds is the square root of 1 plus, remember what it was? G sub x squared plus g sub y squared dA. And we evaluate this as a double integral over the region D in the xy plane. So very similar to line integrals. For line integrals, we stuff the curve into the integral and evaluate it as a Riemann, a regular Riemann integral. For surface integrals, we stuff the surface into the integral and evaluate the resulting integral as a double integral. Okay, let's look at some specific examples. Okay, so example. So here's our example of our first surface area, our first surface integral, which really isn't the first surface integral. Remember, the surface area actually is a surface integral when the function we're integrating is 1. We're not integrating 1 anymore. We're integrating f of x, y, z equals z. So now we're integrating f of x, y, z equals z over the hemisphere z equals the square root of 16 minus x squared minus y squared. So the surface over which we're integrating is the same, involves the same surface we found the surface area of in the previous section, probably about half hour ago. But we're integrating not 1 anymore, we're integrating z. So how do you evaluate a surface integral? Well, let's do it. The integral over the hemisphere of z ds is, how do we evaluate that? We stuff the formula for the surface into the integral. Well, z for the surface area, for the upper hemisphere, is the square root of 16 minus x squared minus y squared. So we stuff that into the surface area, into the function we're integrating. And ds, we already have ds. ds was the square root of 1 plus g sub x squared plus g sub y squared. I'm going to use z's actually just to be even more explicit here. Z sub x squared plus z sub y squared dA, where we now integrate over the projection of this hemisphere into the xy plane, which is just the circle, which we'll get in a minute. But we already have ds. We figured out ds. We figured out, remember that I even highlighted in red for us. ds is 4 over the square root of 16 minus x squared minus y squared. We already did that work. dA. Okay. Over the region D. And what's the region D? Well, the region D is the projection into the xy plane of the upper hemisphere. Well, we get that when z equals 0. So if we take the upper hemisphere of x squared plus y squared plus z squared equals 16, and we set z equals 0 in D, we get x squared plus y squared equals 16. Okay, and that is D. That's the region over which we will be doubly integrated. Now look what happened here. Something nice happened here. Happens here, which doesn't always happen. For our first example, I wanted it to happen. The square root of 16 minus x squared minus y squared cancels, and we just have 4 dA. Okay, or 4. Again, this is a luxury we can't count on very often, but 4 times the integral over the circle of dA. And that's just the area of the circle. It's just 4 times the area of D. Or 4 times, what's the area of a circle centered at the origin? Radius 4. It's pi times 4 squared. Okay. Or finally, oops, not 16, but 64 pi. No units. We can't possibly give units because we don't know what the units of the function f of x, y, z equals z is. So we don't have any units for this. Okay, so this is not surface area. Okay, let's take a look at another one. Let's take a look at another surface integral. Okay, so here's our next one. We're still going to integrate over the hemisphere in the last example. So evaluate the new surface integral. It's no longer z ds, it's x squared plus y squared ds over the hemisphere in the last example. So this over the top half of a sphere centered at the origin, radius 4. Okay, so how do we evaluate a surface integral? We evaluate a surface integral by stuffing the formula for the surface into the function we're integrating and turn that into a double integral. Okay, well, before the function was f of x, y, z equals z. Now f of x, y, z equals x squared plus y squared doesn't involve z. So there's nothing to stuff into x squared plus y squared because the surface is given as z equals a function of x and y. There's nothing to substitute in. F of x, y, and z on the surface is just x squared plus y squared. Okay. ds is still 4 over the square root of 16 minus x squared minus y squared dA. Normally we'd have a lot of work to do because ds can be labor intensive, but we already did that work. And it's now over d, the circle x squared plus y squared. X squared plus y squared. The disk is less than or equal to, what is 16? Okay, just as a reminder. Okay, so how do you think we want to evaluate this double integral? We've converted the surface integral into a double integral, and it looks pretty polar to be kind of explicit about this. It looks like it's saying integrate me using polar. So integrate over the disk x squared plus y squared is less than or equal to 16. Well, if x squared plus y squared equals 16, we're on the boundary, then that means r equals 4. So r goes from 0 to 4. Theta goes from 0 all the way around. X squared plus y squared is r squared. So r squared, 4 over the square root of 16 minus r squared. dA, r, dr, d theta. Okay, so it's real natural for polar. Okay, let's go one more step here before we start using the fundamental theorem. So this is integral from 0 to 2 pi, integral, I can factor out that 4, I guess, 4, 0 to 4, r cubed over the square root of 16 minus r squared, dr, d theta. I've combined the r squared and the r with r from the r dr d theta. This integral, the innermost integral, the antiderivative, happens a lot in our lecture. It also happens in homework and stuff. So just as I did before, I'm gonna go off to the side and evaluate that integral. I don't think you should skip this one. I think you should not skip through this. It's up to you though. This one takes a little bit of ingenuity. Not more than Calc 1. It's kind of the high level Calc 1 integral. What are we going to do? We don't want to let u equal 16 minus r squared because du doesn't appear. Du is negative 2r dr, and we have r cubed in the numerator. Although I think ultimately u equals 16 minus r squared would work with some, maybe a little bit of trickery or whatever, but I'm going to let u equal the entire square root of 16 minus r squared. Okay, but I'm not going to find du right away. I'm going to square to get u squared equals 16 minus r squared. Then I'm going to find the differential of both sides. So the differential of u squared is 2u du equals minus 2r dr. So r dr equals minus u du. Okay, let's integrate. So this integral, antiderivative at least, becomes, well, the numerator can be broken down into r squared times r. And r squared is 16 minus u squared. So this is r squared, 16 minus u squared, over, now the square root is u, and r dr, what's left, is negative u du. You can slow this down if you need. Integral u squared minus 16 du, or 1/3 u cubed minus 16u plus a constant, or 1/3. Now u is that square root, so square root of 16 minus r squared cubed minus 16 times the square root of 16 minus r squared plus a constant. So there's our integration in a cloud. All right, now let's go back to our double integral, our surface integral, which we converted to a double integral. So this is 4 integral 0 to 2 pi. We did our antiderivative work, so I'm going to put that antiderivative in. 1/3 times the square root of 16 minus r cubed, not r cubed, r squared, and that's cubed. The whole thing is cubed, the whole radical cubed. So minus 16 times the square root of 16 minus r squared. As r varies from 0 to 4, that with respect to theta. Okay, so we'll speed this along a little bit. Integral's almost there. This is the integral, 4 times the integral from 0 to 2 pi. If I substitute 4 in the integrand, I get nothing. Into the antiderivative, I get nothing, because 16 minus r squared, 16 minus 4 squared is 0. If I substitute 0 and subtract, I'm going to get minus 1/3 times what? Well, if I put in 0, I'm going to square 16, which is 4. 4 cubed is 64. So I'm going to get minus 1/3 times 64. And then plus what? 64. And it's plus because I'm subtracting. So I think this is okay. Yeah, it is okay. Okay. In any case, we get, what do we get? We get, I'm going to cut to the chase here. This is 2 pi from the integral with respect to theta times 512 pi over 3. You can verify if you'd like to do the arithmetic. Yeah, so you get 10,000, we get 1,024 pi over 3. Again, we can't assign units to this because we do not know, or we haven't assigned units for the function that we're integrating over the surface. Okay. Now, before we move on to our next example, we need to accommodate surfaces that are not given z as a function of x and y. What if x is a function of y and z, or y is a function of x and z? We need to make little adjustments, and they're very easy. They look complicated, but they're very easy to make. So let's do that. Okay, so let's look what happens to the similar case with the triple integrals when we had to consider different types of regions. Type 1 region was surface above, surface below. Type 2, I believe, was surface in front, surface behind. So x was a function of y and z. And then type 3 was surfaces on right and left sides. So we have a similar situation for surface integrals, but the evaluation of the integrals is simpler than the triple integrals were. Considerably simpler, considerably more simple. So here's what we looked at so far. The surface is given z, and I put the surface in red. Z is a function of x and y, where x and y come from a domain in the xy plane. So to evaluate the surface integral, we stuff the z value into the function of x, y, z. So there, you see it in the double integral there, in red, stuffed into the function f of xy and g of xy. We turn it into a double integral over in the xy plane of the reflection or the projection of the surface in the xy plane of the function times ds, which is square root of 1 plus g sub x squared plus g sub y squared dA. So this is what we did so far. So now, what if our surface is x is a function of y and z, and I reoriented the axes so we don't have to look at the function. We don't have to draw the function coming out of the page. So I've reoriented the axes and preserved the correct directions for the axes using the right-hand rule. But what if x is a function of y and z, where y and z come from a domain D in the yz plane? There's not much to worry about here. We're going to make a correction. We're going to make an alteration to our surface area. You're going to make that alteration right in front of your eyes here. So this was the next line here was the line for z was a function of x and y. So what if x is a function of y and z? Well, then we turn it into a double integral, not over the domain in the xy plane, but a domain in the yz plane. And we don't stuff z equals g of x, y, n. We stuff x equals a function of y and z. So let's clear out that integrand. And we're going to stuff in x is a function of y and z. And we're not going to do anything with y and z. Our function is x equals g of y and z. So the derivatives won't be with respect to x or y anymore. They'll be partial derivatives with respect to y and z. So this is all very simple. This changeover. We just let the variables dictate what we do to the integral. Okay. Okay. Well, we have one more case. What if y is a function of x and z? So let's take a look at that. Okay, so let's do this sort of in a mustard yellow color. What if our surface is y equals a function of x and z? So again, I just rearranged the variables on the axes, preserving the right-hand rule. So you're seeing y is a function of x and z. It's not a big deal where x and z come from the domain of the function in the xz plane. So here's our original surface integral, where z was a function of x and y. Let's change it up. We're integrating not over a portion of the xy plane anymore. We're integrating over a portion of the x and z plane. We stuff the formula for the surface into our integral, but it's the y value that's being replaced. So let's get rid of that y value, x, comma, g of x, z for y, leaving z alone. The ds is not 1 plus gx squared plus gy squared. We don't take the derivative of our function of x and z with respect to x and y. We take the partials with respect to x and z. So this change-up is not as drastic as it was for type 1, type 2, and type 3 regions and for triple integrals. Let's take a look at one example where we've changed the orientation of our surface, and then I would suggest a break for you after this, because we have a good 20 minutes, half hour left with lecture to discuss flux integrals. Don't worry about that name yet. But I want to do one more example of these double integral or the surface integrals before we dig into that. Okay, so here's our next example. So here's our example. We're integrating this, or evaluating the surface area, surface integral of z ds, where s is the surface defined by x equals y plus 2z squared. So in this case, x equals a function of y and z, where y is between 0 and 1 and z is between 0 and 1. Well, that last portion tells us our region of integration. So this is our region D. Okay. So x is a function of y and z. So how do we evaluate a surface integral over the surface S of f of x, y, and z ds, where x is a function of y and z? We stuff x as a function of y and z, x equals g of y and z, into the integral, and then we convert it to a double integral. Okay, so it's basically repeating what I had above. We integrate over d in the yz plane of f of g of yz, y and z, where ds is the square root of 1 plus g sub y squared plus g sub z squared dA. Okay, if that's not clear, let's just do it. This is the integral, or our integral now is z ds. Okay, well, the function is x is a function of y and z. So this is x. X equals g of y and z, and just equals z. Okay, so if we're stuffing that into the place of x, it doesn't change anything. This is still z. F of x, y, z is just z. Okay. And I think I've messed up my notation here for a bit. The z is f of x, y, z. Sorry about that. That's why, if it didn't sound right, that's the reason. F of x, y, z is equal to z. Then we stuff x into that. We stuff x equals y squared plus, y plus 2z squared into that, which doesn't change anything. It still stays z. Okay, times the square root of 1 plus the partial of x with respect to y squared. Well, x equals y plus 2z squared, so the partial with respect to y is 1, plus g sub z squared. The partial of x with respect to z would be 4z squared. Okay, dA. And this is over the region D in the xy plane, in the yz plane, where y goes from 0 to 1 and z goes from 0 to 1. So this is a simple iterated integral to set up. Y and z both go from 0 to 1. Okay. And we are integrating z times the square root of 2 plus 16z squared. Okay. We're integrating with respect to z and with respect to y. The order of integration is not important since the limits are constant. Okay, so we don't have to worry about it whether it's a type 1 or type Roman numeral 2 region or whatever. I'm not going to integrate this one on camera. This is a very simple u substitution. Let u equal 2 plus 16z squared. I'll find du. du is 32z dz, and there's where our z dz comes into play really nicely. So this is a very simple integral. If you need help on it, just shoot me an email, and I will perform the antiderivative for you. So here's the dot 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 to indicate I'm leaving that off here. Okay, because we have quite a bit to go in this section, and I want to get moving on it. So this turns out to be 13/12 times the square root of 2. And again, no units assigned, because we don't know what the units, we haven't assigned units for f of x, y, z equals z. So this just has a constant value of 13/12 times the square root of 2. I would suggest a break. I'm definitely going to take one. As usual, the break I take is going to seem like a couple seconds. In reality, it's probably going to be 20 minutes or so. Okay, so we'll continue the second portion of this very shortly. Let's see here. Okay, let's continue our discussion by talking about orienting surfaces, just like we have a way of orienting curves, positive orientation, counterclockwise, negative orientation, clockwise. We can do a similar thing. We need to do a similar thing with surfaces. Now, if the surface is closed, and I've sort of drawn a sort of bell pepper shaped surface here. If the surface is closed, then we call the positive orientation outward. So let's back up a little bit. How do we select an orientation for a surface? We select an orientation for a surface by observing what a normal vector to a surface would do as it varies continuously over the surface. If that didn't make sense, if the surface is closed, we call the outward direction, that is the direction where a normal vector would point in the outward direction, we call that the positive direction. So a normal vector, in fact, we can consider it a unit normal vector. A unit normal vector would be pointing outward. That would be pointing outward would be the positive direction. I think I'm making this sound more complicated than it is. So if a unit vector points outward, that is the positive direction. If the unit vector points inward, that would be the negative direction. So the outward normal, unit normal direction defines the positive orientation. For non-closed surfaces, the situation is a little more complicated. So to get an idea of how to define the orientation of a non-closed surface, let's take a look back at that picture of a surface we considered for surface area earlier. Okay, remember that sort of lime wedge shaped surface we looked at in the last section? I want to construct a normal vector to this surface in a similar way that I constructed the area of the little patch ds of the surface. So let's take a look at two curves on the surface. One of the green curves is where we've sliced through the surface holding y fixed, and then we can draw a tangent vector to that surface. Let's draw a small red tangent vector, similar to what we did before. Okay, so this tangent vector is drawn to the surface, holding y constant. And I'm going to label that one, that tangent vector as A. And I'm going to define A. I'm going to define A to have an x component of 1. So from the tail of A, I'm going to move in the x direction 1 unit. Before I called it dx, that distance. So 1. There is no, the y component is 0. The z component is, remember, to get back to the curve, or back to the sort of tangent line along which I can place this vector, we would move back to the tip of A by looking at the derivative with respect to x of the function. Okay, remember we're holding y constant. Okay, I'm just making sure this is working out. Yeah, this is working out just fine. Then I'm going to form the vector b. Let's see, I think I'll use yellow. Here, another tangent vector. It's not an attractive color. So I'll call that b. And to form it, I'm going to give a y component, second component of 1. So the second component is going to be 1. It has 0 as the first component. There's no change in x. And to get back to the sort of tangent line that I could place this yellow vector on, I would move g, the derivative of g with respect to y. Okay. Okay. So how can I form a normal vector to this surface at the common point of the two tails of these vectors? And I think you probably figured that out. I would use a cross product. A cross B would be a vector that's normal or perpendicular to both vectors. So this vector that I'm drawing here in black is going to be our A, cross B. And I'm going to define that direction as the upward direction, And there's going to be something in the result of A cross B that's going to allow me to just look at the vector, the unit vector that's formed in this direction. So let's find A cross B. A cross B is equal to symbolic determinant ijk 1, 0, f sub x, oops, g sub x, I guess I'm using g for the function, g sub x, 0, 1, and g sub y. Okay. And let's find this cross product. Okay, this is, let's see, covering the first column, minus gx, covering the second column, minus gy, covering the third column, 1. Now this isn't a unit vector. I'd like the normal vector that defines the direction to be a unit vector. So I'm going to take A cross B and divide it by its length to get a unit vector. So I'm going to get minus gx minus gy 1 over the length of the same vector. 1 plus gx squared plus gy squared. Kind of a similar expression here in the denominator. So how can we tell that this vector is going to be a vector pointing upward? We're defining this as a vector that points, we're defining this normal as an upward normal. It is because we have 1 as the z component in the numerator. This is what tells us that we have an upward orientation. Okay, so for an upward orientation, we take a unit vector with 1 in the z component. Okay, before we, of course, normalize the vector, to make it into a unit vector. Okay. Okay, so this is how we define the upward normal, an upward normal. So let's say, let's call this n up. Okay, so how would we define a downward normal? A downward normal would be in the opposite direction. So what do you suppose that would look like? What would n down look like? It would look like the opposite of n up. It would look like gx, gy, negative 1 over the same length. So if we want to define our direction as up, then we look for a 1. We define the normal vector as minus gx minus gy with 1 in the z component before dividing by the length to make it a unit vector. Okay. Now these normals should be memorized because we're going to need to be orienting our surfaces very, very soon. So we have to come up with these normal vectors. That's the bad news. The good news is that really only all you have to memorize is the structure of the first one. So suppose I want to define a normal vector to the right, a unit normal vector to the right. It's very simple. Up and down had a z component of 1 or negative 1. So right and left will have a y component of plus or 1 or of 1 or negative 1 to the left. Okay, to the right is in the y direction, to the left is in the negative y direction. So we would expect a normal the normal unit normal to the right to have a positive 1 in the position of the y variable, the y component. What about the components of x and z? Well, if we're thinking about right and left, that means y is a function of x and z. So we're looking at g sub x and g sub z, both negative, over the length of the vector. 1 plus gx squared plus gz squared. Okay. There's an even better notation you could write. Just a second here. I wanted to make sure I had my notation good before I gave you the simplified versions. If you take a look back at the normal and the upward and downward direction, if we're talking about the up and downward directions, we're considering our surface as z equals some function g of x and y. So we can simplify the notation for the upward normal as minus zx minus zy 1 over the length of the same vector. So I'll just put length with arrows above. Okay. So if we're looking at the downward normal, we're still considering then for either upward or downward orientations, z is a function of x and y. So we would take the opposite of the upward normal. We would have zx, zy, and negative 1, of course, over the length of the vector in the numerator, because we're going to need our normal vectors to be unit vectors, and the reason will become very apparent in the next 10 or 15 minutes. So if I'm considering a normal to the right or normal to the left, that means my function is y as a function of x and z. So if I'm considering right and left, I'm considering y as a function of x and z. So the simplified notation would be minus y sub x 1 minus y sub z over the length of the vector above to make a unit vector. Okay, so what about a normal in the left direction? A normal in the left direction would be the opposite of the unit normal in the right direction. So all we'd have to do is take g sub x minus 1, the opposite of the components before, g sub z, over the length of the vector above. Or in the simplified notation, I go to green here, y sub x, negative 1, y sub z, over the length of the vector above. Okay, well, we have two more orientations. We have the orienting our surface up, orienting our surface down. If we want to orient our surface to the right, we choose a right normal, to the left, a left normal. So what's left? What's left? Front and back orientations. So if I want a normal, unit normal that points in the front direction, if I want a unit vector that points in the front direction, that means I'm assuming that x is a function of y and z. I'm assuming that x is a function of y and z. X will define the front, or the back direction. Okay, so what would I like to happen? How, if you're getting used to this, then you should be able to tell me what one of the components would be and where that should be. If it's in the front direction, that means I'd like x to be positive 1. And then I'd like to have the derivative with respect to y opposite, and the derivative with respect to z negative also, and then divide by the length of that same vector. Or, in simplified form, x is a function of y and z, but we're talking about the front direction, so we'd like the x component to be positive 1 for the front. In the back direction, we'd like x to be negative 1. So in the front direction, x is positive 1. So negative x of y, negative x of z, divide by the length of the vector above. Okay. So one more. Unit normal in the direction of the backwards or back direction. Okay, well, front and back are both x directions. Front should have positive x, positive 1. Back should be negative 1. In fact, just take the opposite of the vector above, or the vector above. Then positive g sub y, positive g sub z, divide by the length of the vector above. Or, in simplified notation, negative 1, then the derivatives should be positive xy, xz, divided by the length of the vector above. Okay. Okay. So just to make sure that you're okay with all this, there's really not 6 things to memorize. Let's do one randomly, and I want to choose a unit normal. Let's say to the left. To the left. Left is the y direction. So is the right. Up, down, z direction, right, left, y direction, front, back, x direction. So automatically, if I want a unit normal on the left, I want to choose not positive 1 for the y component, but negative 1. Positive 1 would be to the right, negative 1 to the left. So what's left? Partial with respect to x and a partial with respect to z of y. Partial with respect to x goes in the x component, partial with respect to z goes in the z component, and the right and the left are the y direction, so our function is y is a function of x and z, and then divide by the length of that vector, y sub z squared. Okay, so if I wanted normal, let's say up, let's say right. No, that's too easy. Let's say front. The reason I said it was too easy because we just looked at left. Front. Front, back are in what directions? Which direction is front? Which direction is front and back? Both of those. In the x direction. Front, the x-axis comes forward and the x-axis goes backwards. So if I want a normal unit normal direction vector in the front direction, the first component should be 1. Back direction, first component will be negative 1. That means the other components will be negative. The other components are the y components, so with respect to y, and the z components, so with respect to z. Front and back, my function is x is a function of y and z. And then divide by the length of that vector. If you already had it, if you already understood it before these examples, I hope you zoomed through these last 2 examples. So let's move forward. What we're going to do to finish up our lecture is to define something that's very, very important in physics and in engineering, physics more generally. They're called surface integrals of vector fields. Very often they're called flux integrals, flux integrals. In order to do this, I've created my own example. This example that I'm going to use in this lecture and in our next lecture, actually, is based on a talk that I gave for our math department a few years ago. I was asked to discuss what's called the divergence theorem with our department. It's one of the last things that Calc 3 students look at, and textbooks don't do a very good job of it. They don't present this extremely important theorem in an intuitive way. So this example is based on a talk that I gave at a department meeting a few years ago. So this is going to be my own discussion of surface integrals of vector fields or flux integrals. Okay. Okay, so let's begin this. So we're going to talk about surface integrals of vector fields or flux integrals. And here's our situation. We have an orange. An orange is peeled and then wrapped in an indestructible screen mesh. Like a screen on a window, just wrap the orange up, but the screen cannot be destroyed. And then we're going to place a firecracker inside the orange and light it. Okay. And what's going to happen? When the firecracker explodes, it's going to push the orange juice out of the orange, but the shape of the orange is going to be maintained because of the screen mesh. Okay, so the problem is to calculate the rate at which liquid leaves the surface. Figure out how fast the liquid is leaving the surface. Okay. So think about it as a tiny person is standing on the surface of the orange with some sort of orange juice meter, measuring how fast orange juice is leaving the surface. Believe it or not, this is an important concept of physics, and it's not usually orange juice that's studying leaving a surface. It could be quantities related to electric fields and magnetic fields and so forth, leaving a surface. Okay. Etc., etc., etc. But orange juice will work for us. Well, we have a few preliminaries we need to talk about. Preliminaries. Let me do this. Very simple preliminaries. Preliminaries. Formulas that we're going to need for this. We're going to need the volume of something from our past that we didn't talk too much about. Parallelepiped. Way back from our beginning. Parallelepiped is just a box, a tilted box. Okay. So let me draw a parallelepiped for us. Okay, so here's a base. Here's an edge, and here's the rest of the parallelepiped. I don't know why I'm dotting that side. So the inside should be dotted. That's okay. Here, parallelepiped. I should dot at those, huh? That's a little better. Okay, so along one edge of the parallelepiped, I'm going to put a vector. Maybe I'll put it in green. Okay, I'm going to call that vector u. It's not a unit vector, so just u. Perpendicular to the base, I'm going to draw another vector. This vector is a unit vector, n hat. Okay, so let's say S equals the area of the base. Let's say n is a unit vector normal to the base or perpendicular to the base. And let's say u, I'm just writing out the quantities, defining them more carefully, is a vector along the edge. Okay, so I want a formula for the volume of a parallelepiped. Not difficult. Volume equals, from geometry, area of the base times the height. Okay, well, the area of the base I said is S. So the height is equal to the component of u in the direction of the normal. You can see that directly. This is the height. Component of u in the direction of normal. Okay, well, we have a formula for the component of u in the direction of normal. This is just S times u dot n over length of n. U dot n over the length of n. This is a formula we learned a long time ago in this course, but it's a normal vector, so the length of n is 1. So I can write this as u dot n times s. Okay, very simple formula. U dot n times s. U dot n times s. Edge. Oops. I've mixed the hats up with the lengths. So u is not a unit vector. It's just an edge vector. N is unit normal. Edge vector dot normal vector unit normal vector times area of the base. Okay, and with that, we're going to be able to do something really amazing. We're going to be able to construct a formula, a very important formula, for the rate at which orange juice leaves the surface here, okay? So let's do that. So I've broken this down into I've broken our goal down into three main components. First, we're going to imagine dividing the orange, the surface of the orange, into an infinite number of little small patches of surface area, okay? Then I'm going to compute the rate at which orange juice leaves a single patch, okay? Then I'm going to sum up all those rates, add up all the rates over all the patches, all the rates at which orange juice leave each of the patches, sum them all up, and that gives me the net rate at which orange juice leaves the entire orange. Okay, so here's a portion of the surface of the orange that I've divided up into little patches of area ds. So let's say ds is the surface area of a small patch of orange. Surface area of a small patch. Very small, infinitely small patch of surface of orange. Surface. Okay. That small, each of those small patches is so small that they're approximately planar. They're approximately flat, like planes. Okay, so we can consider this orange being the surface of the orange being divided up into a whole bunch of little flat, literally flat planar patches. Okay, so let's let v be the velocity of the orange juice at a corner of the patch. The speed of the orange, or the velocity of the orange juice at the corner of a patch. We'll identify a specific patch. Okay. So let me put that velocity vector on here. Let's see, I want my velocity vector to say be red. Okay, so let's say the orange juice is passing through this corner in this direction. And the length of that vector tells you the speed at which it's passing through that orange in that direction. Okay, so here's our v vector, velocity vector of the orange juice. Okay. Okay. Now here's another assumption we kind of have to make. We're going to assume that the patch is so small that the orange juice is constant throughout that patch. The rate of the speed of the orange juice is constant along that entire patch. So I could place that velocity vector anywhere in this patch of area ds. Okay. So if I could place the velocity vector here or here or here. In fact, I want to place them there. I want to place them there also, or anywhere within the middle of this patch. Okay, let me get rid of those. Okay, and again, why can I do that? Because the patch is infinitely small. There's not enough area for the velocity to change that much. So it's approximately constant in that whole patch. So let's say that n is a unit outward normal at the corner. Unit outward normal at the corner. And I want to draw that vector. Okay, so n, I guess I'll use black for that. It's a unit outward normal. So the length of that vector is 1. Okay. I want to define dv sub patch as the amount of orange juice leaving the patch, that entire patch, leaving the patch in time, very small time, dt. Okay. Okay. So I'd like to describe the distance that the orange juice has traveled in that small time. So the distance that the orange juice has traveled in that small time is the magnitude of v times dt. This is something we learn in pre-algebra. Rate times time equals distance. The magnitude of v is the speed at which orange juice leaves that corner or that entire patch, since we're assuming that the velocity is constant in that really tiny patch. So rate times time equals distance. I could bring the dt inside. So v dt, the length of v dt, is the distance that the orange juice has traveled through that patch in time dt. Distance the orange juice travels in time dt. Okay. So now I want to figure out the amount of orange juice leaving the patch in that small amount of time. Well, if I'm assuming that velocity vector v, that red velocity vector v, is constant throughout that patch, and that's a reasonable assumption because the patch is infinitely small, then orange juice will be pushing through that patch in the shape of a parallelepiped, of a tilted box. So I'm going to draw that. Okay. Actually, I have to be a little more careful with that. Let me get rid of that dotted line. I need to scale down the velocity vector by dt for the distance that the orange juice travels. So I'm going to scale down the vector v by multiplying it by dt, and I'm going to write that in green. So that scaled down velocity vector, that green vector is the distance that the orange juice has passed through the patch in time t. And I'm going to use that to construct a parallelepiped, which gives the amount of orange juice leaving the patch in time dt. Okay. Gosh, my drawings are horrible. I haven't learned how to draw better in 30 years of doing this. I can't really complain. It's actually much worse in my first 5 years. Okay. So that little green parallelepiped is the amount of orange juice that's left in time dt. I want to find a formula for that. Okay, so I want to find a formula for the amount of orange juice that's left the patch in time dt. Okay, that's equal to the volume of the parallelepiped. It's the area of the base. Times the height. Now I could use the formula that I developed in the preliminaries, or I could just rederive it. It's very easy. The area of the base is ds. Now the height is the component of v dt in the direction of the normal. The component of v dt in the direction of the unit vector n. Okay? Okay, just like in the preliminaries. Okay, so this is ds times v dt dot n over the length of n, which is 1. I'm going to rearrange these items. So this is v dot n ds dt. Okay. Now, remember my goal. My goal is to figure out the rate at which orange juice leaves this patch. The rate at which orange juice leaves the patch. I have the volume that's left the patch. The rate I get by dividing by dt. So dv patch over dt is v dot n ds. Now you're probably getting the idea, or getting a good idea of why this discussion takes place in chapter 16. This is a very, very difficult discussion in defense of your author and the author of every other calculus textbook. This is something that it is seen in physics courses, and I don't think it's in any calculus textbook, primarily because the background of the authors of textbooks is not physics, and I've had a lot of physics, so hopefully this is making sense to you. Okay, there is a bottom line here. I'm not going to have you derive any of this, but this is a derivation that would take place in a physics course. So if you're not understanding the derivation, it's not essential. In any case, this is the rate at which orange juice leaves a single patch. So the net rate of change of orange juice over all of these patches is the sum of all these individual v dot n ds's. So the rate at which orange juice leaves the entire orange. Now notice I've taken away the subscript of patch, is the sum. How do we sum elements of v dot n ds? We sum them by considering the surface integral over the entire surface of v dot n ds. Okay, this is the rate at which orange juice leaves the entire surface of the orange. It's also called the flux of the velocity vector across the surface S. For this reason, this is called a flux integral. Flux integrals measure the rate at which a quantity of substance leaves a surface. A flux integral gives you the rate at which a quantity of substance leaves a surface. Okay, there's a notation, an alternate notation for this, and it's a very common notation. It's very common to label n ds as ds for surface area, but as a vector. Okay, so if you label nds, the unit normal times the differential element of surface area, then you can rewrite this flux integral as v dot ds. I'm uncomfortable with it, but it's extremely popular. I'm uncomfortable with viewing surface area as a vector, but you can visualize d surface area as a vector quantity, where the length of ds is just the area of the patch of the surface, and the direction of this is normal to the surface. Okay. We're going to end this long lecture, finally. That's the good news. The bad news is with an example. Okay, so let me write up the example, and we'll power through it, and we'll end the section. Okay, so here's our last example. Let's get through it. So I want to find the flux of the vector field F. Now, the vector field F could represent velocity or a number of other physical interpretations of a field. So find the flux of the field F across the surface S, where the formula for F is negative xi minus yj plus z cubed k, where S is a part of the cone z equals the square root of x squared plus y squared between two planes z equals 1 and z equals 3. And the orientation is downward. So I've drawn a picture of the cone, the portion of the cone between z equals 1 and z equals 3. And we have a downward orientation. That means that if I'm on the surface of the cone, that the unit normal vector will have a z component of negative 1 before normalizing, before dividing by the length of the vector. Okay, if you don't remember that, or if it doesn't ring a bell, let's find the unit normal vector first. Okay, the unit normal vector n. Okay, and now we're looking for a downward orientation is going to equal, well, if it's going to have a downward orientation, it's going to have a z component of negative 1. And that means that the other two components will have positive coefficients, zx, zy, over the length of the same vector, over 1 plus zx squared. Oops, I don't need the length symbol then. 1 plus zx squared plus, plus zy squared, square root of. Okay. Okay. So let's find that normal. Well, the function is z equals x squared plus y squared to the 1/2, I believe. That was it. Yeah. Okay. So z sub x is 1/2 x squared plus y squared to the negative 1/2 times 2x, or if you will, x over the square root of x squared plus y squared. So c sub y will be similar. It'll have y in the numerator. So our normal then, it's going to look kind of big at first here. Let me see if I can squeeze this in here. Our normal vector then will have components z sub x, x over the square root of x squared plus y squared. Z sub y would be y over the square root of x squared plus y squared, similarly, comma, negative 1, all over the length of this the vector in the numerator. So over the square root of 1 plus x over the square root of x squared plus y squared. It simplifies nicely in a bit. Squared plus y over the square root of x squared plus y squared squared. Okay. Okay. Let's do the square root bar. So this is, well, the denominator simplifies very nicely. The denominator simplifies to the square root of 2, and the reason for that is the two terms the two terms with the x's and y's simplify to x squared plus y squared over x squared plus y squared, which is 1. Okay, so this simplifies into 1 over the square root of 2 times x over the square root of x squared plus y squared, y over the square root of x squared plus y squared, proportion negative 1. Okay, you can stop the video if you want to confirm that that's 1 over the square root of 2. If that didn't make sense, it's no big deal. It's take you a couple seconds to figure that out. Let's compute this flux integral. So the flux of this vector field across S equals the flux integral, the surface integral over the surface S of f dot n ds. Before, we were looking at the flux of the velocity of the orange juice over the surface of the orange. So it was the surface integral of v dot n ds. So the flux of f is f dot n ds. Okay, let's compute this. So this is the surface integral. Well, what does f look like? I'm going to use the bracket notation. So it's minus xi minus yj. I think it was z cubed k, okay, dot n, 1 over the square root of 2, times x over the square root of x squared plus y squared. Now these flux integrals tend to be symbol heavy. A lot of writing. Okay, so I'm writing out the normal vector again. And ds, which we have not computed yet. ds is the same differential element of surface area that we started this lecture a couple hours ago on, okay? Okay, so let's compute this dot product. So the 1 over radical 2 can be brought out in front of the integral. It's just a constant. And let's perform this dot product. This is negative x is the first component, and x over the square root of x squared plus y squared is the first component in n. So we have minus x squared over the square root of x squared plus y squared. Okay, minus another y, so minus y squared over the square root of x squared plus y squared. And then minus z cubed, all ds. This is a surface integral. This is f of x, the surface integral of f of x, y, z ds. This is what we started this section with. Okay, and how do we evaluate surface integrals? We stuff the formula for the surface into the function and convert it into a double integral. So this is 1 over the square root of 2 times the double integral over the region D in the xy plane. We'll look at that in a minute. Then we put the surface. Remember, the surface is z equals the square root of x squared plus y squared. You stuff the surface into the formula. So we're not changing the first two terms here. The first two terms we can write as minus x squared minus y squared over the square root of x. We're combining them into one expression, x squared plus y squared. But it also this function also contains z, so we stuff the surface, square root of x squared plus y squared, into the function we're integrating, and then multiply by ds. The ds is the square root of 1 plus z sub x squared. Well, z sub x, we looked at that already. That's z sub x squared plus lots of writing with these z sub y. This should start looking familiar. dA. And that we've seen that quantity under the square root. It's 2. So this is the square root of 2. This is all the square root of 2. And we happen to have 1 over the square root of 2 out front. Okay, so we're getting there. So this is the double integral over the region D. And again, we'll come back to the region D in a bit. This is a major setup here for polar. It's a major polar integration formula going on here. So x squared plus y squared cubed. It's simplifying quite a bit. dA. So if our region is a natural polar region, we're in good shape. Let's take a look at what D looks like. D is a projection of our surface into the xy plane. Well, I should do that maybe in green or something here. D is outside this little green circle I'm drawing. We're only looking at the portion of the cone lies above z equals 1 and below z equals 3. So Z, or D rather, is this donut shape, flat donut shape, I guess. Technically, it's called an annulus. It's the area between two circles. So that's our region D. So this is a natural polar region. So what are the limits on D? Well, the surface is z equals the square root of x squared plus y squared. Well, when z equals 1, I'm looking at the unit circle. So this says x squared plus y squared equals 1. That's the inner circle. What about when z equals 3? When z equals 3, I have 3 equals, finding the intersection. 3 equals the square root of x squared plus y squared. That gives you the circle of radius 3. Okay, so I'm going to slip those in. In polar, the inner circle is r equals 1. The outer circle is r equals 3. So let's integrate. Let's change this into a polar integral and get this lecture done. Okay, so let's switch to polar. So this is minus r squared over r. X squared plus y squared equals r squared. Minus r cubed. dA is r. dr. d theta. R goes from 1, the inner circle, to 3, outer circle. Theta goes from 0 to 2 pi to get us all around this annular region. Okay, I'm going to take this integral one more step, and then I'll cut to the answer, because it's a very simple integral. So this is 0 to 2 pi, 1 to 3, innermost integral. And r squared over r is r, times the r and r dr d theta is minus r squared. And then r cubed times r is minus r to the 4th. And I'll stop the integral there. Those are easy powers. To integrate, dot, dot, dot. The answer, and you might want to try to verify this. There aren't too many homework problems from this section, I don't think. So you might have time to verify this answer. Or you just go to homework. There's a similar flux integral from homework. Minus 1712 over 15. And what would the units of this be? What would the units of this be if we were, what would the units of this be? It's a rate at which quantity leaves a surface, a quantity of substance. So it's going to be in cubic units. That's volume per time. It could be hours, seconds, or whatever. Flux gives you the rate at which quantity leaves a surface. Okay, so it's cubic units per second. Right, cubic units of, I wonder if I have that right. Cubic units, yeah, I think that is right. So it's as if we place the firecracker inside of this portion of a cone. Okay. And that takes us to the end of our lecture, folks. So get started on homework right away. Our final exam is coming up very, very soon. And I'm looking forward to talking with you all again soon.